Our purpose now is to prove that the MST algorithms that we seen are correct, and we're going to do it in several steps. The first step would be to show that all the safe edges must appear in all MSTs of the graph. So, and we're going to call this the cut property that we will define shortly. So if E is a safe edge, then every minimum spanning tree contains E. To remind you, for sake of simplistic exposition, we're assuming that all the weights of the cost of the edges in the graph are distinct. So that's not an issue. Okay, now the basic idea of the proof is very simple. We have the MST, right? And we have this edge E that somehow is not in the MST. This is E, and somehow it's not in the MST. But E is a safe edge, right? That means that there is some cut that it's the cheapest edge in the cut, right? So the basic idea is that there must be another edge in the tree that belongs to the same cut, and we can just throw this edge away, or try to throw it away in this case. Let's say this edge, and put the new edge instead, right? So this is an exchange argument, which we encountered before for greedy algorithms. So that's a natural thing to try. The thing is that this doesn't always work, so you have to be a bit careful about it. So let's do a first try. Again, the important thing we are using here is the fact that this edge is safe for the cut, as such the cheapest edge in the cut, as such the edge that we threw out, right, the edge we threw out was more expensive, right? That's where we use the safety, we get a new spanning tree which is cheaper, right? So that's the basic argument. Okay, so we have to be a bit careful. This is the written argument of what I just said. And the problem is that if you do it non-carefully, strange thing can happen. So here's an example. You add the edge F here to this graph. Okay. And this edge was added because, let's see why it was added. Yeah, it was added because it's safe for this cut, right? This set against all the other edges, it's safe, right? It's indeed the cheapest edge between the science set and the complement. Okay, so we want to edge this edge to the MST, so we add it in, and then we throw away some cut edge, some other cut edge in the current MST. This edge, for example, is in the belongs to the current spanning tree, and it's in the cut, right? It's more expensive than this edge, so makes sense, right? Let's just throw it away. Let's throw this edge away and put F in. But if you do that, of course, what would happen would be that we will get this graph, which is no longer connected. No. So that's not good. So we just have to be slightly more careful. So how are we going to be slightly more careful? What we're going to do, we're going to look on the new edge that we are putting in, right? And then we use the fact that this is a tree, right? We define the tree as a graph such that between any two vertices there is a unique path. So there is a unique path here between the two vertices. It's P, and the important thing that P and E together form a cycle. And now we are good to go, right? Because think about it, we have the set S, we have this cycle. One of the edge of the cycle is this edge E that we are trying to insert. So this cycle, this P plus E, this is the cycle. This cycle must contain an edge that is in the cut and is on the cycle, right? The previous mistake was that we took an edge that was somewhere in the spanning tree. Here, no, we are taking an edge on the cycle that is formed when you add E and is a cut edge, right? Formally, what we do, we start traveling from one vertex along this unique path to the other endpoint, and as soon as we encounter an edge that is in the cut, we take it, right? And now we eject it, right? We can now afford to, this is the green edge, and we put in the new edge, and we throw away this old edge, and we get this new spanning tree. which is indeed cheaper, right? And we were allowed to do it because we threw away an edge of cost 15 and put in an edge of price 9, and we are guaranteed to do this because this was a safe edge, and as such, it was cheaper, right? The edge that was thrown away was more expensive. So that's very good, right? Because we just proved that it must have been that this edge was already in the minimum spanning tree. Otherwise, it wasn't the minimum spanning tree. Okay, we need to prove that indeed this exchange operation worked, right? So that this new graph is indeed a spanning tree. So the more interesting property to prove is the connectivity. And the connectivity argument is very simple once you get used to it. So we have a cycle, we have a path P, and an edge E, the edge that we're inserting, right? The important thing to remember is that this pipe P is part of the spanning tree, right? Now, the important observation is that if you take a cycle like this one and delete an edge, for example, this one, what remained is still connected, right? Because we have a path and it still connects all the vertices. So inserting E creates a cycle, but removing an edge leaves a path that is still connected. As such, if we take a spanning tree, we insert an edge, we introduce a cycle, and then we break the cycle by taking away an edge, the connectivity of all the vertices that were on the cycle are still connected in the graph without this deleted edge, right? So the connectivity of all the vertices that were on the cycle, they were connected before we did the exchange, and they're connected after we did the exchange. As such, the graph is still connected. So that's the connectivity. The second thing that is important is that it's still a spanning tree, but this is easy, right? Because we started with a graph that have n-1 edges, we removed one edge, we inserted one edge, we end up with a graph with n-1 edges, it's connected, and as such it must be a tree. The reason is because we proved earlier, if you remember, the tree has n-1 edges. So if this graph had more edges, so we know it has n-1 edges. If it wasn't a tree, and we know it's connected, if it wasn't a tree, it means that we could delete an edge and get a tree, which would imply that the tree has less than n-1 edges, which is a contradiction. Okay, so this graph is, after the exchange, is both connected, it's spanning, and as such, it's a valid spanning tree, and it's a cheaper spanning tree, which implies indeed that we just proved that a safe edge must be in any minimum spanning tree of the graph.